Okay guys, we'll get started. So last Thursday, we had a little bit of a look at classic nucleation. All right? Hopefully you recall we utilised our basic knowledge of thermodynamics, okay, defining the difference between the free energy of, just as an example, the liquid-solid transformation, okay, and how we define those, and how we can assign the driving force to nucleation being relative to our degree of undercooling, delta T. Okay, so the greater our delta T, typically the greater our driving force for nucleation. We looked at classic nucleation theory, okay, defining a solid or another phase emanating from another phase within a fixed volume. Okay. We looked at the simple example of a spherical embryo of the new phase forming, okay, and we were able to define in terms of its critical radius, okay, the driving force for its formation and continued growth or stability, okay, and we found that this is basically defined by the ratio of its volume, okay, which is giving us a more negative free energy, okay, or driving force, a lower free energy, versus the surface area that's competing against us, our positive contribution, okay, looking at our interfacial free energy, or comparing to our interfacial free energy, and how the combination of these can give us basically our delta G star value, okay, so our critical free energy required for the stability and then the growth of a nucleus, and the critical radius R star. We also looked at heterogeneous nucleation of solid from the liquid, okay, when we have to include factors associated with, for example, a mold wall or even a foreign particle. Okay. And how we can see that free energy associated with heterogeneous nucleation is typically much, much lower than that for homogeneous nucleation. And we had the different parameters associated with, for example, the mold wall. We had a little bit of a look at nucleation rates. I wasn't going to dwell too far on that. Basically, the main takeaway was, for heterogeneous sites at least, the more sites that you have, obviously the higher the nucleation rate. We also looked at the case of the precipitation, or the nucleation and growth of a solid phase within another solid phase, okay, where we had to take into account this new misfit or lattice strain parameter, okay, which actually pushes our negative driving forces to a little bit more positive territory and change the shape of this curve compared to just the liquid-solid transformation due to having to include this misfit strain energy parameter. Right, and again, the nucleation events there. And we also had a look at some specific sites that could act as heterogeneous nucleation sites, and how the likeliness of the nucleation of a new phase was relative to the amount of disorder or trapped energy at that local site. Right. So we did look at, the cases for grain faces, grain edges, grain corners. Right. And we also spoke a little bit about how difficult it is to nucleate within the bulk phase itself, okay, where there are no defects, or when there's a defect such as a vacancy or a dislocation. It's also easier to nucleate inside the grain, but always much, much easier at the grain boundaries where we have a greater number of defects. All right. So the next part we're going to talk about today, and you were given these notes with last week's lecture series, okay, is transformation observation, and in particular growth. Okay. So when we have our solid phase, we've established a stable nucleus. Now it's time for the forward reaction to proceed. Okay, so we've nucleated, great. We've gone through our stochastic process of nucleation. We've got stable nuclei. Now it's time for that phase to grow. Okay, so the forward reaction is now going to proceed, okay, at a rate that's defined by the growth rate of the actual crystal. Okay, so how does crystal growth occur? So it's a series of processes where a specific atom or a molecule or an ion, okay, is incorporated into the surface of a growing crystal, okay, causing it to increase in size. Right? So we've got our stable nucleus. Now we're taking atoms or molecules from the surrounding environment, okay, they have to diffuse to the surface of that nucleus. They're going to add to that nucleus, and it's going to begin to grow as we add atoms to it, atom by atom, essentially. Okay. So the process of crystal growth can be summarised into 4 steps, right? Transfer of atoms through solution. Okay, so atoms have to come from the liquid or from the solid, right, to that site. Okay, so this is a diffusion-based process. Okay, these atoms then have to actually attach themselves to the surface or molecules. Okay, sometimes that's not as easy as it seems. Then we have essentially, often, the movement of these atoms or molecules across the surface. Okay, and that what they will do is find a site of lower energy, which we'll get onto in a second. Okay, and this usually involves the attachment, stage 4, attachment of these atoms to edges or steps or kinks on the surface of that nucleus. Okay, so we think about a crystal, right? What's a crystal? Let's just think of a really basic cubic crystal lattice. Right? When you have a crystal lattice and a spherical embryo, right, because it's essentially squares, right? Think of 1980s, excuse me, 1980s video games and things like that. It's all heavily pixelated. To make something that's round, it's still going to have steps on the edge, yeah? It's the same with a crystal, right? So we might have a spherical embryo, but of course, at the very, very surface there, it's going to be stepped. Okay? So steps in the surface provide sites of slightly lower energy for atoms to actually attach. Okay, so the first process, the so-called transport process, is diffusion-based, okay, whereas steps 2 to 4 are referred to as surface processes. And they might involve several sub-steps, okay, transporting across the surface. Some will detach because they might find a local site back in solution that's of lower energy. Some might reattach and then continue to move across the surface. Right? Since these overall crystal growth kinetics steps, since these different steps normally occur in series, the slowest process will control crystal growth kinetics. Right? So we're already starting to define a couple of different steps or processes that might control the kinetics, and hopefully this kind of meshes with what Jason was telling you in the first couple of weeks. Right? So we've got our nucleation step. That can be a rate-defining process. If nucleation is slow, okay, until the actual crystals can start to form and grow, right? So that's one rate-defining step, okay, and then the actual growth process itself, which has several steps within it. Okay, so for example, we might have a limited amount of atoms or molecules coming from our solution, right? That might be a rate-defining step. Okay, if the concentration is low, then the diffusion of atoms from great distances can become the rate-defining step. Okay. If the surface of the crystal is particularly difficult for an atom to move across, all right, this might happen on specific crystallographic planes, things like that. That could be your rate-defining step. Other things can actually speed it up. If your nucleus or site might be highly strained within the lattice, okay, it can put itself, it might grow with defects in it, and then those defect sites could be sites for atoms to actually attach to much more quickly. And that would not then be a rate-defining step. That's a very, very fast step. All right? So there's many different steps within this growth process that can define our overall growth kinetics and the kinetics of our reaction. Great. All right. So let's have a little bit of a look at crystal growth theory. Okay. So what we've got here is a schematic representation, okay, of the process involved in crystal growth. All right. Now take note of this because we usually pop this one into the exam as well. Okay. There's 7 specific steps for slow growth in crystals. Okay. So what we have is step 1, which I've already started to define here. This is the transport or diffusion of a solute to a position near the crystal surface. Okay, so our atom or our molecule, right, is coming out of our solution, liquid or solid, could be either, okay, and migrating towards the surface of our growing phase here. Step 2, diffusion through a boundary layer. Okay, so often, and particularly in solids, immediately above the surface of our growing phase, there could be things like stress fields. Okay, so in a solid-solid growth scenario, there could be a stress field from the new phase growing. That stress field could make it harder or easier for this molecule or atom to pass through this boundary layer. Okay, or there could be a chemical concentration gradient that affects its mobility through this boundary layer. Okay, so we have to kind of be mindful that there are surface effects there. And I guess it's similar to our gamma parameter, all right? Our surface energy parameter for the nucleation phase. Right? There's always some kind of stress or something going off very close to the surface, okay, which this atom has to also overcome to be attached to the surface. All right? So once we've overcome this boundary layer scenario, we come to step 3. And this is adsorption or attachment to the crystal surface. All right? For this process to happen in a metal system, that's relatively easy. Okay? But for a molecular system, an inorganic system or something like that, sometimes there has to be a transfer of either an atom, okay, for attachment to the surface. So sometimes we've got ordered structures or we've got chain structures and things like that. So sometimes this molecule might have to get rid of an atom or an ion or an electron for this attachment event to occur. Okay? Sometimes that can be a rate-limiting step. Right? Sometimes it can also make it impossible. Okay? Sometimes this molecule might be compatible in a certain shape, okay, to attach to this surface. It might have to modify itself, or essentially what can happen, it will then be ejected. Right? Step number 4, okay, which is sort of involved with that ejection step as well, this 4-star step. We have diffusion over the surface. So once we've attached, okay, our atom or our molecule then has a choice to move across the surface or detach from the surface. Okay. Remember, this is an equilibrium process as well. Sometimes if there's a high concentration of molecules at the surface, or again some kind of incompatibility, or perhaps a high concentration of these atoms or ions that had to be ejected for attachment, this molecule or atom might detach. But for the case of growth, let's just say we've got attachment. Right? So step 4, we now can diffuse across the surface. And the reason we'd have an atom or a molecule diffusing across the surface is it's searching for a lower energy site to be attached to. Okay? Hopefully you can appreciate that if we sit an atom on top of a flat surface, okay, essentially it's only making, for argument's sake, one bond, okay, with that surface. All right. So this is a high energy configuration, having an atom sticking up in space, okay, as something's trying to grow. To minimize that energy, it's going to migrate across the surface until it finds a site where it can bond in more ways to the material to assist in growth. Okay. So this is where step number 5 comes into play. So the attachment to a step or an edge. Okay, so hopefully you can appreciate an atom or a molecule will then diffuse across the surface, find a step or an edge in the structure, okay, and then essentially it's got 2 sites to bond to, okay, or another edge or something else to bond to, right, which makes this a lower energy site. We can see here on our energy diagram as we're progressing through these phases, okay, so diffusion until we reach the material, overcoming the boundary layer requires a little bit of energy, but then we're minimized again. Okay, attaching to the surface requires energy, but once we are attached, we are reducing the structural energy. Okay. Diffusing across the surface and finding an edge, okay, requires energy, but once we do find the edge, we're lowering the structural energy. All right. So, yeah, attachment to a step or an edge is the next step. Okay. And then what we find happens after this, okay, we can get diffusion along that step or edge. Again, this atom or this molecule is searching for an even lower energy site to attach to. Okay? And often what we'll find is once it finds that lower energy site, which is going to be a kink or a step or a vacancy, okay, so a kink in this edge or this step, again providing another surface for that atom or molecule to bond to, okay, making it even more stable and lower energy. Okay, and this is is step 7 here, right? Lowering the energy of the structure, where it will eventually come to rest. Okay? If there is no step or kink in the surface, it essentially will create the next step or kink for the growth process to occur. All right. So this process will occur over and over again on multiple surfaces on the crystal. Again, if we're starting with a spherical embryo, it's obviously going to start off with a lot of these steps and kinks within it as it's growing, providing lower energy sites for these atoms to attach to or diffuse to reduce the structural energy. Okay. So one of the most commonly used models, okay, was provided by Kossel. Okay. And basically, we consider this growth process of consisting of cubic units. Okay, the easiest way to describe it and model it. All right. So using that process that we've just explained, we can explain it in terms of these cube-type Kossel diagrams. Right? The model envisages the crystal surface as being made of cubic units, which form layers of monatomic height, limited by steps or edges. These steps contain a number of kinks along their length. Okay, so there's a kink. Okay, there's an edge vacancy. Okay, this is a step, and here's a surface vacancy. Okay, the area between steps is referred to as a terrace, and it may contain single absorbed growth units, clusters, or vacancies according to this model. Okay, so as we see here, we see this cube growing in the middle of our step on our terrace, okay, on the surface. If it's stable enough, it can start to grow its own crystal sections. If not, it will diffuse and find a lower energy site. And this goes on and on until we build up the crystal. Okay. So hence we can see that kink sites or edge vacancy sites can provide the lowest energy site and offer the most stable growth configuration. Okay, so typically, as you probably would have guessed, growth then proceeds by the attachment of these growth units to these kink sites, steps, and edges. Okay, the kink will move along the step, producing a net advancement of the step until it reaches a face or an edge. Then a new step will form by the nucleation of a new monolayer from a 2D nucleus. Okay, so that's what we would call a 2D nucleus up here. So this growth mechanism is normally referred to as multinucleation or multilower growth or birth and spread growth. Okay, so birth and spread growth is the first type of growth that we're going to be talking about today. And again, this is the very, very slow mechanism. All right. Something that also happens in this birth and spread type growth is we might have actual defects within our material that are also assisting in this growth. Okay, so we've already spoken about nucleation being interfered with, or heterogeneous nucleation being favoured at sites of deformation or vacancies or just flaws in our crystal structure. Okay, the most common type of flaw in our crystal structure is a dislocation, and we can have different types of dislocations. Okay, edge and step dislocations. They have a different structure and makeup, okay, and orientations, right? But essentially what they do is provide a pre-step or flaw in our material. Okay, and by having this pre-step or this flaw in our material, it's already providing us with essentially a growth site or a step. Okay, so again, using our cube diagrams, Kossel diagrams, we'd have our atom or molecule attaching to the surface, and then it would be seeking out one of these steps or regions of higher structural energy to attach. Okay? So we can, from these types of defects, screw or edge dislocations, get some very, very interesting types of growth patterns evolving, right, on our surfaces of our crystals. Okay? But the main takeaway here is that defects also provide sites for accelerated growth. And we kind of know this, and it also comes into play with recrystallization processes as well, that a material that does have a deformation or a strain in it that is producing a flaw, the reaction rates occur faster. Okay? If we have a completely relaxed and annealed material, okay, the growth rates are essentially going to be slower. Okay, so the birth and spread type of growth, okay, typically produces nice smooth surfaces. And we do have a couple of different types of growth regimes, and they're basically distinguished by the speed at which they do grow. Okay. So if we have a look at them in terms of their growth rate, okay, producing smooth surfaces, we have spiral growth or birth and spread growth regimes. Okay, and then in terms of producing a rough surface, we have this adhesive growth. Okay. These types of growth mechanisms are occurring when our free energy for growth is relatively low. Okay, so we haven't got a great deal of undercooling in our system, for example. All right. We might be fairly close to our melting point, or we're cooling at a very, very slow rate. For adhesive growth, okay, driving force for solidification and growth is going to be very, very high. Okay, so we might have very, very high undercooling or very, very large cooling rates. Okay, and what this does is it invokes this adhesive growth. So here we have molecules or atoms coming very, very quickly to our surface, growing wherever they attach, and not enough time for them to diffuse over the crystal surface. Okay? When these atoms don't have time to diffuse over that crystal surface to attach to lower energy sites, we get rapid growth in a specific direction, or we get rough surface growth. This is the basis of growing of dendrites and dendritic structures in materials. Okay? So if we have very, very high undercooling, very, very high cooling rates, okay, atoms must attach, they must grow, don't have time to diffuse to form nice smooth surfaces or spherical crystals, aqueous crystals. Okay, so they just attach as best they can. And as we mentioned previously, they attach on very specific planes of the lowest energy first and grow very rapidly from those. So that's why we get these plate structures or needle structures or dendrite structures. Okay, so here we've put some, I've put some examples of various images. Now these are AFM, atomic force microscopy images, of crystal growth surfaces. Okay, and these are examples of spiral growth or the birth and spread growth mechanisms. So very, very slow growth on a crystal surface. And that's actually what it's looking like. Okay, so these here are essentially atomic planes. Okay, that's an atomic step. So at very, very high resolution here, we can see the atomic steps as these crystals are growing. All right. So this one here, this is obviously our spiral growth mechanism. Okay, so basically we've started from a single point. This crystal started to grow, okay, in a certain manner based on energy and the shape of that nucleus. Okay. Similar with this one here. Okay. Here we've got multiple birth and spread sites. Okay, so we might have had a molecule deposit here, an atom deposit here on the surface. This has progressed to grow locally at different sites. Okay. Hopefully you can appreciate these orientation relationships for the crystal structure. All right, so we might be on specific planes here of a cubic structure that are preferred attachment sites for atoms for crystals to grow. Here we have one that might be on an FCC type structure. Okay, we've got 60-degree angles as preferred growth planes, 90 degrees. Okay. This one here is parallel. Okay. And as we mentioned before, often these can be associated with dislocations and things. Dislocations, screw dislocations might invoke a spiral type growth, because screw dislocations themselves have a spiral or rotation factor about them in their strain fields. All right. Edge dislocations might provide steps as well for them to attach to. So many examples there of this slow growth or birth and spread type growth in crystals. Okay, so that's our observation of slow growth, all right? But again, we have to kind of switch back to reality, okay, in being able to observe and measure these things. All right, so we can observe the end product, of growth, something like this. And from this, we might be able to start to discern the growth kinetics. Okay? These crystals might have been given X amount of time to nucleate and grow, or they might have been observed for the nucleation and growth steps. Okay? And it's these things that we're measuring or visualizing, we can actually see, that we then go and revert back to classic nucleation theory. Try to fill in the blanks. So thermodynamics, okay, is essentially just a method, okay, of describing things. Okay, describing events, describing chemical events. All right. We've assigned a unit to it, joules, kilojoules, whatever you like. Again, it's all based on observation. In terms of what we would utilise in the lab or in industry, okay, phenomenal nucleation and transformation events are usually plotted in what's called a TTT or a CCT diagram. Okay, so a TTT diagram is temperature, time, and transformation diagram. That's what it stands for. Or CCT stands for continuous cooling transformation diagram. Essentially one and the same thing, just depending on which axis you're taking as the most important to your study. All right? But what these actually describe is what happens, what nucleates, what grows relative to time in a given chemical system. Okay? To produce one of these diagrams, yeah, there is some kind of thermodynamic software that we can use to produce them nowadays. But again, we kind of need our initial data or inputs to generate them. Right? So let's have a little bit of a look at them. Have you seen these diagrams before in first year courses? No? So you've got no idea what this squiggly thing on the board is? Okay. All right, so let's break it down. This one's actually a fairly complex one, but it's the most common one used in industry. Okay, it's all about steel. All right, so we know what our steel's made out of, iron and carbon. All right, putting carbon in our steel invokes many different phase transformations. Okay, so what we have on one axis is temperature. All right, and on another axis we have time. Time's usually on a log scale because these transformations can take a very, very long time at low temperature. Where they would typically start, and this may not be the best example, on our temperature axis we have a few different events that would occur. Yeah? What would those events be? Temperature. If we heat a material up, what happens? Yeah? Yeah. So probably the most important phase transformation that we would know and that occurs in many systems is melting. Okay, so we start at the solid state, heat it up, go up in temperature, it'll melt. What happens if we go even further in temperature? It'll boil. Okay? We all know these transformations. Okay? So these sorts of transformations can be plotted on these diagrams as well. Okay, we're not limited to temperature and time. We can also put pressure on these diagrams as well if we really want to. But we're going to stick with our TTT diagrams for today. Okay, other things can happen. Okay, other types of transformations. So you might know when we have a steel, low or high carbon steel, specific steel. If we cool it very, very quickly, we can get other things occurring, can't we? Yeah, we can get metastable transformations. Okay, martensite or bainite forming. Yeah. The steel system itself goes from a high temperature phase, an FCC phase, and when we do hit around about between 800 and 700 degrees, we get a transformation from austenite, FCC, to ferrite, BCC structure. Okay, so even solid state transformations we're plotting on these diagrams. But, as you know, all of these types of transformations, or most of these transformations, also require nucleation. Right? Nucleation and growth essentially take time. Okay? So what we end up with, dependent on our cooling rate or heating rate in our system, is a whole bunch of these lines that identify where these transformations occur. Do you have a question with that? No? Cool. So essentially we can plot our cooling rate from high temperature, and this here is just an example of a possible cooling trajectory or a quench of a steel. Now, if we take this steel, for example, and this is probably a low carbon steel or medium carbon steel by the look of this, right? We cool it down over time. Right? We might heat our steel up, throw it into a bucket of water, right? And this is the cooling curve that we generate. Okay? So within about 100 to 1,000 seconds, we're cooling from 800 degrees all the way down to room temperature. Okay? We can see this curve here, within this curve here, that at high temperature we're going from this austenite, FCC phase. Okay? We're passing through transition, okay, into our equilibrium phases, which would be over here. Right? But we're not cutting through these boundaries here. Okay? So what happens is if we cool this down fast enough, we retain this austenite structure all the way down to room temperature. We might get to a critical point where austenite must transform into, say, martensite. Right? And if we keep cooling fast enough, we retain that martensite at room temperature. So the entire structure of our steel is now martensite. Right? However, if we sit at room temperature for a number of days, years, or whatever, we actually start to cross over these other boundaries where we get the equilibrium phases, such as our perlite and ferrite. If we cooled much, much more slowly from over 800 degrees or from the melting point, which would be way up here, we essentially would just pass through these equilibrium phases, perlite, cementite. All right? So basically the idea of these diagrams is for us to put into context these transformations in a useful way. Right? In industry, we might want a material that is soft, so we would cool it more slowly to go through the soft ferrite phase. We might want a material that's very, very hard, would be brittle. Okay, so we'd cool it very, very quickly to avoid the soft phases and invoke these harder phases over here. Yeah?
On the diagram it says MS and MF. What does that mean?
Martensite start and martensite finish temperatures. Okay? The martensitic transformation isn't diffusion based, it's just a translation of the crystal lattice, and that's why it doesn't have curved lines and it's got straight lines. Okay? It only requires a certain amount of energy, it's not time dependent.
So what is that gap between austenite and martensite start? What's happening to the molecule at that point?
So below the A1 line, we are retained austenite. Okay? As we hit the martensite start line, okay, this is when our crystal structure is starting to transfer into martensite. Okay? And once we're below the martensite finish line, right, this is when we've got permanent martensite. Also comes into play for shape memory alloys, because the martensitic transformation, that is essential for all of those alloys. It's also different on the way up and the way down. Okay? So we know that we must go above the MS temperature to completely convert or dissolve all of our martensite, for example. Okay? So it still is kind of an equilibrium. If we only go to, say, 200 degrees in that diagram, we still have some retained martensite in our structure. If we went up and then went back down. Okay, so that one probably wasn't a great one to start with because it is a very, very complex system. Most of them are a lot simpler than this. Okay, so I'll just rehash here that some of these transformations are diffusion dependent. Basically, anything that has a curved line in our system is diffusion dependent. Okay, straight lines are not diffusion dependent. Okay, so these are our martensitic transformations, which are just a translation of a crystal lattice. So here's our simpler version. All right. This is the type of phase diagram that I'd use. Okay, so I work in the amorphous alloys side of things. Okay, and this is looking at just basic nucleation and growth events. All right. So in this type of diagram here, TTT diagram, yes, we typically with our materials would start in the liquid state. Okay. Usually all materials are going to be produced, or metal materials at least, are going to be produced from a melt. Okay, at the foundry, or even at the blast furnace, we're melting our material, and we're shaping it into something more useful or refining it into something more useful. Okay? And typically, just by nature, what would normally happen is we're cooling from the liquid phase. Okay? We're going below the melting temperature. Okay? And we can see here we've got this curved line here. Okay? Time on this axis, don't forget. And then after some period of time, as we're dropping temperature, crystallization starts. All right? So I'll ask the question there, what's probably the event or the rate limiting step for crystallization to actually start there? If we are undercooling before crystallization starts, what's our rate limiting step? Nucleation, yeah. Okay? So eventually, as we keep progressing in this time axis here, this curved line here would come very, very close to our melting temperature, okay, until we hit infinite conditions or equilibrium conditions, okay, where at the melting point crystallization will occur. Right? But if we're moving faster than that, okay, nucleation is our rate limiting step. Okay, so we have this gap where we're in a supercooled liquid state or undercooled liquid before crystallization occurs. Okay, so at time 0, okay, in a typical casting setup where we're casting large sections, low cooling rate, could be using a sand mold or even a steel mold or something like that. Start at 0, our curling curve would probably move something like this. We'd move below the melting temperature, we'd hit crystallization and continue on. Our material solidifies. Yeah? Depending how fast we drop is what our growth type would be. Okay? Birthing growth, spiral growth, or rough growth or dendritic rapid growth. However, and this is where this diagram becomes a little bit more significant, if we can cool from the liquid state, okay, and not give the system enough time for nucleation and growth, we essentially remain in this supercooled liquid region until we hit our glass transition temperature. Okay. At the glass transition temperature, we change or alter or relax. Essentially, the system relaxes into what's called a vitreous solid state. Vitreous solid state is your window glass, your metallic glass. Okay? Anything that you know of as glass is typically in a vitreous solid state. Most polymers are also in this vitreous solid state. Okay? So basically, they've been cooled, okay, at a rate faster than nucleation and essentially crystal growth can occur. The most stable supercooled liquid known on the planet is, does anyone know? It's a pretty obvious one if you think about it. What material stays glassy for a very, very long time? It's very, very easy to maintain a glassy state. Glass, okay. Silica, okay. SiO2, silicate glass. It's the most stable glass there is, okay. Just because of its chemistry and its crystal structure, or the molecular structure to be more accurate, okay. Silicate glass is very, very stable and has this rotational degree of symmetry about its molecular structure or its preferred covalent structure that lets the energy between the crystal and the supercooled liquid be almost equal to one another. Right? And it literally takes centuries before silicate would even think about crystallizing at room temperature. So with this glass transition line here, you'll also notice that it's curved, right, to an extent. So over time, over a long, long period of time, this glass transition temperature would start to approach maybe room temperature or something like this, or whatever your holding temperature is. Okay, so eventually, over a long, 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 long period of time, or even a short period of time, depending on the system, this line will touch the temperature that you're holding at, and the material will crystallize, because the supercooled liquid state is metastable. It's not stable. It's not the equilibrium state. Okay. So with window glass, this line here is very, very flat. Goes for a very, very long period of time, way off the board there, before crystallization would occur. Okay. It's because it's very, very difficult to nucleate and also grow silica, crystalline silica, from the vitreous silica. With metals, however, Okay? The nose of this TTT curve is very, very close to 0. Okay? So this is why we see very, very few amorphous metals. All right? Essentially, they will crystallize very, very quickly. Okay? Aluminium, for example, will crystallize 10 to the minus 6 seconds. It begins to nucleate and grow as crystals. Silver is actually the fastest metal to nucleate and grow. Aluminium is not too far behind it. The others are typically somewhere in between. Now, any questions on this type of TTT diagram? This is the most basic case. So we kind of get it, kind of get how it works, temperature and time. All right, so once again, any material, we can heat it up to above its melting point, and then we can cool it down again, okay, below its melting point and through various stages of crystallization. Okay. So the way that I like to explain some of this is with the metallic glasses. Okay, so this is nucleation and growth, or the lack of. Okay, both ways. All right, so we've had a little bit of a look at this diagram so far. So you've probably never even heard of a metallic glass. Okay, has anybody ever heard of it? No? They're not really in use. Like Apple holds a lot of the patent rights. I think they made a couple of SIM card ejectors out of metallic glass. There are a few mobile phone components made out of it because they are very, very strong and very elastic. The most common use of metallic glass, however, is actually in transformer cores. Okay? Do we know anything about magnetism? So magnetism has to do with the specific spin orientation of electrons within, usually, an ordered crystal structure. Okay? An ordered crystal structure can exacerbate magnetism by, I guess, expanding the magnetic moments of electrons in a nice ordered structure. That would give us hard magnetic properties. Okay? If we actually make a material that's amorphous, okay, we still have these magnetic moments of these elements, okay, but we don't have this crystal order anymore. It's amorphous. It's not quite random, but it's definitely not crystalline. Okay? By having the dispersion of these magnetic moments throughout the material, we can get extremely good soft magnetic properties. And these are used in transformer cores. They have been used in transformer cores since about the 60s because they are the softest magnetic materials known. But, okay, and we take a quote from Mike Ashby. Hopefully you've all gone and bought Ashby and Jones for your first year materials courses. Okay, so Mike Ashby out at Cambridge, he puts metallic glasses down as the most significant development in the material science world since the discovery of plastics over 50 years ago. And we'll get on to why he'd compare them to plastics in a moment. All right. So what are they? They're multi-component metal alloys that exhibit no long-range ordering on an atomic scale. Okay, so they're not crystalline. So here we have a typical crystal lattice. That's that one there's basically the cesium chloride structure. Okay, BCC ordered structure. Okay, very, very ordered cubic domains. Okay, compared to amorphous, where we essentially have only ever some form of chemical or topological short-range order, no long-range order whatsoever. Okay, I don't use the word random because they're not perfectly random, but they're pretty close. All right. So I'll back it up just quickly. So when we actually cool our metal down quickly enough to avoid this crystallization nose, we end up with a vitreous solid below the glass transition temperature. Right. Their structures are homogeneous. Okay, so there's no local composition variations from forming multiple phases. It's a single phase. They behave more like ceramic glasses or polymers than conventional metals. This is to do with their structure, yeah? Okay, they have a glass transition temperature, just like a silica glass or like a polymer. They can be brittle, just like window glasses can be brittle, or they can be very tough. All right. I usually just flash this slide up just so that you can have a little bit of a look at the actual performance of these materials compared to crystalline materials. All right. So again, we've avoided crystallization. We've got an amorphous solid. Here I've plotted yield strength versus the Young modulus of the materials. Okay, and we can see here, here's our regular alloys, titanium alloys, high-strength steels, nickel-based superalloys, stainless steel, all these, magnesium alloys. Okay, they follow this 0.65 elastic strain limit trend down here. They're all crystalline. However, the metallic glasses follow this line up here. Okay, and we're essentially getting close to some of the strongest, at least metals, if not materials, on the planet. Okay, so yield strength over 5 GPa. Alright. So mild steel, does anyone know the yield strength of mild steel? Roughly about 200 MPa. That's down here. There's mild steel. Okay, so these materials are essentially already here. They're 10 times the strength of mild steel. Okay, more closely 20 times the strength of mild steel, for example. Okay, and that's just due to that amorphous structure. They've also got this elastic strain limit of 2%. Again, that's due to structure, but hopefully you can appreciate something like a polymer, even an elastomer that's amorphous, okay, or vitreous, okay, usually has a very, very high elastic limit compared to a crystal. All right. We can also see that a metallic glass can be very, very tough. Here's our fracture toughness of this palladium-based glass up here, okay, and here's our regular silicate and oxide glasses down here. Okay, this has to do with the bonding. We've got metallic bonding there instead of covalent bonding. All right. Okay, so a quick look into amorphous materials and avoiding nucleation to give us glass formation. So a conventional alloy, something like an aluminium alloy or a magnesium alloy, steel, something like that. Okay, the nose of our TTT curve would look something like this. All right. Crystallization occurs in a very, very short time space. Okay, within the order of a picosecond or something like this, we start to see nucleation and then growth. All right. So as we cool, cooling rate of 1,000,000 Kelvin per second, which is very, very fast. Okay, we're always going to essentially cross this line and start to crystallize. We can see here that this part of the line here is very, very close to the melting point. Yeah? The metallic glasses, however, okay, where they begin to nucleate and grow, crystallize, happens much, much further along in our time scales. Okay, so this is typically in the order of 100 seconds and things like that it takes for nucleation to occur in a metallic glass. Okay, so at cooling at 100 Kelvin per second, we can still avoid crystallization, okay, cool below the glass transition and get a vitreous solid. So this kind of raises a question for us, okay? Why do some alloys form metallic glasses and others don't? Can anyone think of a reason? What would the differences be in something that's heavily alloyed, okay, something like a metallic glass composition that contains a lot of different elements of different sizes? Yeah. So basically, when we have a system where all the atoms are the same species, or the same size, diffusion becomes very, very easy. Okay? We essentially only have to break similar bonds, okay, for an atom to move. These bonds can be highly dissociated in the liquid state. And the packing of atoms that are all the same size, or spheres that are all the same size, actually isn't great. We can't achieve efficient or ideal packing when we've got atoms that are all the same size. Okay, so there's gaps between them. When you've got gaps between atoms, it's easier for other atoms to move through the system. Okay? That all affects our diffusion, which then in turn affects our crystallization kinetics, yeah? Okay, so all liquids or metallic glasses are not simply this random jumble of atoms. They exhibit very specific chemical and topological short-range order in both the liquid and vitreous solid state that help minimize structural energy, so it's still about energy, and when competing with crystalline phases. So forming the metallic glass then becomes this kind of battle, okay, between the structure the liquid, or the structure of the glass, okay? And the thermodynamic driving force and energy associated with the crystals, equilibrium crystal structures or metastable crystal structures the system wants to form, okay? So can we make this structure here have an energy, structural energy similar to an ordered crystalline structure? Okay. And can we jam atoms in space in such a way that they don't want to move away from this structure to create this structure? So in a ternary alloy, if we've got atoms that are 3 different types and 3 different sizes, you can see if they're all jammed in there tightly and filling in all the gaps, it's actually quite difficult to try to form this binary crystal structures. Okay? The blue ones have to kind of get together with the green ones to make this in a specific way. They've got to get all the red ones out of the way. Okay? So this affects our diffusion, and this affects our nucleation kinetics and growth of crystals. So, well, we've got this thermodynamic driving force for crystallization for a given system, which is essentially set. Okay? Again, thermodynamics is all observational. What is the structural energy of this crystal? X kilojoules per mole. All right? We can create some compositions where the liquid structure is also exceptionally stable. Okay? We can do this by minimizing atomic bomb distances or having chemical combinations that like to sit next to each other but not necessarily at specific angles like in a crystal. All right? Something else that's an indicator of liquid stability. Okay? Do we know what a phase diagram is yet? Hopefully you've learned about phase diagrams in first year. Yeah? Do we know what a eutectic reaction is? Yeah, what does it look like in terms of our composition map? Do we all know? We all remember? Draw it on the board. Okay, simple system. Element X, element Y, melting point of element X, melting point of element Y. Okay, what would a eutectic look like between these two? Some change in composition? Yep, something like this. Very basic eutectic. Okay, so here we have liquid plus X, here we have liquid plus Y, here we have X plus Y. Yeah? What do we notice about this point here? A eutectic reaction point. Its melting point is lower than both of the pure metals to start with. And sometimes, in certain systems, it can be much lower than those two melting points. That tells us that at this very particular composition, from the bottom up, crystallization of X and Y, driving force competing with the liquid, is relatively low. And from the top down, the structure of the liquid at that composition is very, very strong or low energy. Okay, so these cluster structures, short-range order structures, are very, very stable at that composition. Okay. Thermodynamics down here is described. Thermodynamics up here is never described. Hasn't been. If you actually go back and look at Joey Gibbs' formulas and theories on thermodynamics, one of his first two assumptions is all atoms are the same size and liquids are random. Okay? Both of those statements are incorrect. So we only know really what's happening under here because we can observe the solid. The liquid's very, very hard to observe structurally. Yeah? But at these eutectic points, we know that the liquid is going to be quite stable relative to crystals. So that's what we look for in a system that's easy to undercool and form a vitreous solid. All right. So that's the thermodynamic side. Let's have a little bit of a think about the kinetic side here. All right. So it's been shown that a higher viscosity or lower the diffusion rate, these two things go hand in hand. If our liquid has got a high viscosity, okay, think about viscosity. How thick is your liquid? Okay. Our diffusion rates are going to be low. It's harder for atoms to move through a viscous material. Okay. So the higher the viscosity, the lower the diffusion rate in an LML, and the slower the nucleation kinetics for crystallization, and the higher the propensity to form a glass when cooling. So how can we ensure a high viscosity and a low diffusion rate? This actually comes down to this, what's called the atomic packing efficiency of the liquid. So liquid alloys that have a highly efficiently packed atomic structure. So if we think about our atoms as a geometric hard sphere, okay, with metals this is an okay assumption. Metallic bonding is usually non-directional or fairly non-directional. Okay, so in a hard sphere model, an atom that is in direct kissing contact with every atom in its first coordination shell. Okay, so if we take an atom in our liquid, right, every atom in its first coordination shell, so every atom around it, no matter how big it is or small it is in direct kissing contact with that atom. All in contact. So that's the first condition. And then every atom in that first coordination shell is in direct contact with each other. Imagine that in 3 dimensions if you can. All right. Essentially that means that all those atoms are jammed in space. Okay? We've got global efficient packing. When that occurs, it's very difficult for atoms to move. When atoms can't move or diffuse, they can't rearrange themselves to nucleate and grow a new phase. So, think about it in terms of structural energy, large differences in atomic spacing beyond the equilibrium atomic bond length, okay, create distortions in energy or increase the energy of the system. If we try to push atoms too close together, okay, our energy profile is increased. If we pull them too far apart, their energy profile is increased. They have this optimum bond distance. So if every atom in that structure there wasn't in kissing contact, we're increasing the structural energy of the system, yeah? Okay. So having them all in perfect contact or having a specific atomic radius that allows the packing of them in that configuration minimizes structural energy. Gaps equal energy. If you've got gaps in your structure, it's a higher energy structure. And again, we just spoke about it, kinetics, okay? If the liquid or the solid has this densely packed configuration, it's difficult for these atoms to move around. Right? So energy and kinetics, we're satisfying 2 conditions to stop crystallization to occur. Right? If the structural energy of the liquid is very close to that of the solid, okay, the driving force is smaller. You might, from our first slide in our classic nucleation slide, remember we had our free energy of our solid and our free energy of our liquid plotted on the same plot. Essentially those 2 lines are very, 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 very close together in these systems. So you have to move a long, long way or provide a great deal of undercooling to increase the driving force for crystallization in these systems because of that very, very low difference in structural energy between the 2. So what is this really like in reality in our liquid? Okay, so say we have a 3-component system. Okay, atom A, atom B, and atom C. Right? Atoms A, B, and C have different sizes. Having different sizes allows us to have a different number or a greater number of packing configurations where atoms can touch one another, okay, and be jammed in their structure. It's very, very specific, okay? The number of each of these atoms and the radius of each of these atoms becomes very specific to satisfy those conditions, okay? But they can be satisfied. It's a basic geometric equation. We can actually calculate, all right, if we have clusters of atoms of the exact same composition, okay, with different atomic centers, we can pack all of those atoms around those atomic centers to satisfy this packing efficiency. All right. And when we achieve that, okay, essentially our liquid can't move easily. The atoms are all jammed in there. And the driving force for it to move is quite low. Okay? Why move away from a stable configuration with all these atoms in contact to try and form a crystal if you don't have to? Okay? So they're the conditions that need to be satisfied for nucleation from the liquid. Okay? or avoiding it if we can, to form a vitreous solid. All right. This guy here wrote a big Nature paper about it once upon a time, okay? But that's basically the crux to it. All right, so the key takeaway there is, right, if we can minimise the structural energy of the liquid and minimise the diffusion kinetics of the liquid, we can avoid nucleation and growth if we want to in some systems. All right, that's a matter of chemistry and topology. Okay, so something else that we do use in industry that might be a little bit relevant to what you've just learned. Okay, so viscoelastic forming of non-crystalline materials. The key advantage of having something that's amorphous is sometimes it's strength, sometimes it's see-through, okay, but sometimes it's the formability. Okay, so a material has to be useful for an application, all right, but in terms of being industry viable, you have to be able to make it and form it. And the easier you can make it and form it, the more money you make as a company, yeah? So, amorphous materials display this crazy thing called our glass transition temperature, yeah? So if we know, we take a silicate glass, window glass, we heat it up, it becomes very, very soft. It's still very viscous, but it's very soft, yeah? So we can kind of blow it into different shapes with a force, you know, as tiny as a human lung. Okay, human lungs aren't very strong in retrospect to other industrial forming processes. But if we heat up our glass, we can blow it into shapes, okay, like this quite easily, very low force. Right? So this is, you know, highly attractive to industry, being able to form something very, very easily. When we cool it back down to room temperature, it's very, very strong. Okay, sometimes it's see-through, which is another advantage. Or at least it's sealing, okay? So we utilise, you know, the Newtonian fluid behaviour of thermoplastics and of glasses above their glass transition temperature for forming. So a PET bottle, very, very easy to blow a plastic bottle. That's why we've got a huge waste problem, yeah? Easy to make, easy to store things, and easy to throw away, I suppose. Okay? Similar with glass bottles, and that's why it's been used for so long. All right? 200 years ago, what were we making bottles out of? Only a very, very small amount of bottles were made out of glass 200 years ago. What was the primary way that we would contain a liquid? Ceramics, yeah? Fired ceramics. So we'd make a clay vessel, okay? We'd make a clay vessel. We'd have to make it, okay, as a green form. We'd have to glaze it. We'd have to fire it to make it strong enough, okay? And then we'd have to put a cork or something on top of it, all right? As things progress, technology-wise, okay, we can get machines to make bottles much more quickly out of glass, okay, without these additional steps of glazing. Okay, we don't have to glaze a glass; it's already glazed essentially, okay, and we don't have to do a secondary firing step or painting or anything like this. All right. So, having that glass transition is very, very useful for industry, almost essential. All right. Same for metallic glasses. Okay, as I said, people are starting to use these things a little bit now, and we are utilising the glass transition temperature to form them. Okay, we'll get onto that in a little minute. Okay, so unlike any other metal, metallic glasses exhibit this glass transition temperature as well, just like a silicate glass or a polymer. Okay, above which they form into a supercooled liquid, where their viscosity dramatically drops. Okay, so I don't know if anyone's ever done any glass blowing, okay, but once you go above that glass transition temperature, it's like playing with glue tack or chewing gum. Okay, very, very easy to manipulate. All right, here's a couple of examples of metallic glasses above the supercooled liquid, above their glass transition temperature for forming. Okay, so this one here is straight out of my PhD many years ago. Just a tensile sample made out of metallic glass. We heat it up to 165 degrees. We can stretch it several thousand % of its original gauge length. Yeah. This one here is a Chanel No. 5 special edition perfume bottle made by Jan Strouwers out at Yale University. Okay. You can probably see down the bottom here. So this is a blow molded tube made out of a gold-based metallic glass. Okay, so this is made out of a gold alloy. that's vitreous solid, metallic glass. This disc here is the original preform. Okay, so making a disc of material with that diameter and that thickness, we were able to blow mold this shape out of it, or this shape. Okay, so blow molding bottles out of vitreous solids. All right. Here's another example of that blow molding. Now there's no metal, no crystalline metal on the planet that you can form to that degree. Okay, they always work harden and then they'll fracture and crack. Okay, so having this different structure is very, very advantageous. We can even now put, I don't know if you recognize this character here. Who's that? Anyone know? 1990s sci-fi, 2000, I don't know. T1000, yeah, liquid metal man. Okay, we can now put shape memory, crystal particles into these alloys, the supercooled liquids, and they can change their shape on their own, just with temperature and electrical current running through them. Okay, so this technology is still a long way off. Okay, but basically we're starting to get there with doing tricky things with material science. Sidestep. Okay. So we've already had a little bit of a look now at these TTT diagrams and how we can utilize them in cooling. We can also use them in this superplastic forming of vitreous materials. All right, so what we have to do, and those of you that have fallen asleep, I suggest you wake up because this one will be an exam. All right, what we have to do, okay, at room temperature, we're below this glass transition temperature, yeah? To form the material, we have to then heat up. And we're on a ticking time bomb, so to speak, before we hit this crystallization curve when we're above TG. Okay, so what we have to do, we have to heat the material up, get above the glass transition temperature where it relaxes and we can form it like chewing gum, and then we have to quickly cool back down before we hit the nose of that crystallization curve. So now we have our vitreous solid again, but it's now been shaped into something useful. Yeah? We also know that with temperature increases, our viscosity decreases. All right? So it's always this trade-off. How far above TG do we go to reduce the viscosity? When we reduce the viscosity, the extent to which we can work the material increases. Okay, but we also then have to cool it much more quickly to avoid this nose. So there's a couple of different pathways that we can take. Okay? But all the time, we have to avoid crystallization in these vitreous materials. Okay? It's the same with polymers and silicate glasses, except this nose is way over here in our time scales. All right. So we have options. We can do a slow forming process. We heat up just above TG. Viscosity is still relatively high, but we've got a lot of time to form our material and then cool it down. Or we can go rapid resistive heating, for example, even close to TL, form it into something completely different, but then we have to rapidly quench, again, to avoid the nose, or somewhere in between. Okay. Hopefully you guys understand that one. That's one that I get questions about 2 days before the exam every year. Okay. And again, it is all about nucleation. It's all about growth, but it's an applied case for thermoplastic forming. Yeah?
What would happen to the material, like if you have your little test tube of metal and you're trying to blow it into your perfume, what happens if you hit that crystallization point? Does it just like rapidly proceed to form material?
So once crystallization occurs, those crystals will grow. But it's, in terms of formability, it becomes a composite structure. Then those crystal nuclei are now in the way of Newtonian flow or viscous flow. Okay? Basically, once you exceed 10% crystallized volume fractions, you start to see tearing in the
So
material.
you know you've hit the crystallization hump if you've got tears or like clumps?
Yeah, so two things. You might be exceeding the flow rate of the material, which is viscosity-based phenomena, okay? Or you're changing the flow rate of the material by inducing these particles, which creates localized shear around the particle. Localized shear leads to tearing. Or you can observe it. You'd experimentally observe it. You can do differential scanning calorimetry. You can see when the crystals start because there's an energy signal transferring from the vitreous solid to a crystalline state. It's an exothermic reaction. Okay. All right. So we finished up early. I didn't take a break because I knew we were close. But there's still, again, a lot to take in from this lecture. Okay. I suggest, okay, the last 2 lecture sets, you learn that very, very well for your exam. Okay. I think significant parts of questions 2 and 3 in your exam come from those 2 lecture sets. Okay. So understanding it is critical. And again, we will have a final tutorial going over these things if you've got any other questions as well. Okay? But in the meantime, any questions? Either come up now or send me an email. Other than that, have a nice day.
Explain this again because I didn't really understand.
Okay. So what we have, so this is our TTT diagram,
Yep.
sure. This axis temperature, also viscosity
Yep.
inside, okay, and this is time.
Yep.
So from the first time I described the diagram, we're talking about missing this crystallization curve
Yeah.
upon cooling.
Yep.
So you understand that one?
Yep.
We're cooling down, we're missing it, so we've got a vitreous solid.
Yeah.
We're ending up down here somewhere.
Yep.
All right? So we've got a lump of material now that is very, very hard,
Yeah.
maybe a little bit brittle. That is the shape that we've cast it in, essentially.
Yeah, okay.
And it's the same for like pellets of polymers or glasses that we want to turn into something else. So what we do, we take that material, and now it's still on the same diagram wherever we finished up.
Yeah.
Okay, say this point here. To form it again, what we have to do is heat up and go above the glass transition temperature.
Okay.
Okay, so this is where it transforms from this vitreous solid, something as hard as window glass,
Yeah.
to a supercooled liquid,
Yeah.
where it's as viscous as chewing gum. Right? So that's what we're doing. We're coming along with our material, we're heating it up above TG, and then as we're increasing with temperature, we've also got to remember this axis here,
Yeah.
viscosity. So viscosity decreases
Okay.
as we get hotter.
Okay.
Right? So what we've got here is 3 different types of processing that we could do. We could do a very, very rapid heating, okay, to a very, very high temperature, below TL, okay, where the viscosity is going to be very low,
Yep.
and we can do a large deformation. So we might be able to transform our lump into another very complex shape. Because it's got low viscosity, it can flow very well
Yeah.
into our dye. Okay?
Yep.
But because we've gone so high, we also have to cool very, very quickly to
Okay.
avoid that crystallization
Right.
noise.
Okay.
Right? And then these are just intermediates. We can cool it at slightly lower rate, heat it at a slightly lower rate to slightly lower or lesser, viscosity.
Yep.
Right? And then we can cool it down at a slightly lower rate.
Okay.
As long as we're missing that nose.
Yep.
And this one here, this one's going to be probably for less complex sorts of geometries and things. We can heat it just above the TG,
Yeah.
deform it over a very long period of time
Yep.
before we hit that crystallization curve and then cool it down slowly.
Okay. Yeah. Okay, thank you.
Okay. Okay.
Kind of confused.
Yeah, no, if you've never seen them before,
Yep.
they're going to be confusing.
Okay.
Okay, so what we have here on this axis is our temperature.
Yep.
Yep, and on this axis we have time. This is usually on a log scale, okay? Because we're talking from very short time frames to very long time frames. So the first time that we've showed you this diagram this morning, we were talking about cooling from the liquid state. Okay, if that's our melting point there, we always start from up here and we cool very, very quickly to avoid hitting this crystallization nose here. Okay, as soon as our cooling profile would hit that, we got crystallization. Right? The same thing happens from low temperature as well. This is essentially just a cumulative timeline of our material. Okay? So if we're going to cool from the liquid down into the vitreous solid, going through our supercooled liquid state, here we've got a lump of material. Okay, and this could be like a pellet. So the preform for making polymer bottles and things is just pellets, little plastic pellets, and then they mash them together and form something out of it. Similar with some glasses as well, lead light and stuff like that. So from cooling, we've got our pellets or our lumps in this state here. Now, if we want to actually form them, and form them very, very easily, because remember, in this vitreous solid state, it's just a brittle piece of glass. We can't really shape it into anything. We can grind it, but that's about it. What we want to do is, again, we want to heat it up. To get it to be able to move, again, we've got to go above our glass transition temperature. So it goes from being a vitreous solid like glass to a supercooled liquid like chewing gum. So when we heat up glass and polymers, very stretchy, just like chewing gum. All right. Once we're above that glass transition temperature, as we increase in temperature, what's happening is our viscosity is decreasing. So if we heated up our material very, very quickly to a very high temperature, still below the liquidus temperature, the viscosity is going to be very low. So we can do very large deformations, make very complex, shapes very quickly. All right? But we also have to then cool very, very quickly from that high temperature, again to avoid this known as a crystallization curve. Right? And these other lines here, these are just different routes that we could take. Okay? Instead of heating very, very quickly and getting a very low viscosity, we might, our process might only let us heat it up at this rate. Okay? We might only be able to go to this point here where we have a bit lower viscosity than in this case. Okay? So maybe we mightn't be able to deform it as much, or mightn't be able to get as complex a shape. Okay? And then again, we have to cool it down before we cross over that boundary, form a crystal. Right? And in this blue case, this is where we're working at very, very close to the glass transition temperature. So the viscosity here would be fairly high compared to this case. Right? But we've got a very, very long time period that we can deform for. Right? So it might be less complex, but we might be doing a very gradual, large deformation. Right? So we would heat it up just above TG, sit it at a fixed temperature, and again, this might be a limitation of our equipment. It might be a large muffle furnace or something like that that doesn't have this rapid heating capacity or rapid cooling capacity. Okay, so we can only heat it slowly. We can hold it at temperature for a long period of time and then only cool it slowly. Right, so we would choose that path. But again, in each case, we're not crossing over that transformation curve, that transformation line there. Okay.
We're not crossing that crystallization. Is it because you introduce cracks when you?
No. This is nucleation and growth.
Yeah.
Okay.
So
this is nucleation. It's dependent on temperature and time, how much undercooling we have. So remember delta T from Thursday's lecture. Yeah. Okay. Here, in terms of this time, we can have a large delta T, right, before we crystallize. Here, delta T becomes smaller and smaller over time. All right. So no, this here represents this nucleation process and then crystal growth. All right. And remember, it's diffusion driven. Okay, diffusion affects the kinetics. If the atoms in the liquid are very difficult to move around, then where it starts to crystallize, this curve shifts much, much further in this direction here. Okay, if it's easy to crystallize, then it's way over here.
Okay. Yeah.
Okay.
That should be fine.
Yeah, thank you.
Okay.
Could you please explain to me about the eutectoid composition again?
Yep. Okay, so basically we know from thermodynamics, if we look at a phase diagram, and there's different ways like computer methods and things now that we can model systems using thermodynamics. Right? When we have a eutectic reaction, okay, it represents two things. All right. So basically, for elements X and Y at this composition here, the driving force of forming this phase and this phase are the lowest at that composition. All right. So that's from the crystal side, and that's how thermodynamics would describe it.
Okay.
All right. But there's also a contribution from the liquid phase as well. Okay, so at this composition, or very close to it, the liquid phase is also very, very stable. Okay.
Oh, is that why the driving force is very low because the liquid is very stable?
Mm-hmm.
Oh.
Yeah, and at these compositions, the liquid's much less stable, the crystal's more stable. So it's always a competition between the two. Many people forget about L, the liquid. Okay, and they just focus on the solid here and the crystals, and treat that as a phenomenon, but it's really got to do with the competition between liquid and solid.
Oh, I see.
Okay.
And for this graph,
Mm-hmm.
why does we have to plateau first at the 100
so
second?
so it's cumulative. Okay, so a transformation in terms of time starts from where we solidify it. Yeah. So at time 0, and this is a log scale, so we don't have 0, but we've got a very, very small time increment here.
Okay.
Okay, so if we cast this material, okay, it follows this cooling curve like this, yeah? And we might finish up here, so 10 to the minus 2, which was basically where we said our cooling rates were, way back here. Yeah, 10 to the minus 2. 10 to the 2, all right? So, it's arbitrary where we start, all right? But do you understand how we've only got a certain amount of time before we actually hit that crystallization curve if we're heating?
Is it because if we heat it too high, it has less distance to the nose because
If we heat the system, what we're doing now is letting the atoms become mobile again. Okay, so in the vitreous solid, they're kind of locked in. Okay, viscosity drops very, very rapidly below the glass transition temperature, so atoms are locked in. When we heat it up again, okay, the structure relaxes once we're above the glass transition temperature. So bonding becomes a little bit further apart. Some bonds no longer occur anymore. Right? So now this material is a supercooled liquid. It now has a viscosity like chewing gum instead of window glass. Right?
Okay.
But because the atoms are now mobile, we've only got, again, a certain amount of time. Okay? So if we're heating it up, remember our timer is always ticking. Tick, 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 tick. So we're heating up, heating up, heating up. Time is elapsing. Okay? Once we're above TG, it relaxes. We can form it, do some forming process. And then we go, okay, we're very close now. We have to cool it. Because if we go over this line, we're going to start forming crystals. So we have to cool it back down below TG again. Below TG, the atoms don't move very quickly.
it cannot form crystal, so it cannot nucleate to form crystal.
Yeah.
Oh, I see.
Okay.
Okay, thank you so much.